we will need to keep our information organized. As we analyze the function, because we remember we're going to be starting with equations and trying to find the graphs. Are there any tools you have learned in a math class or really any class to help you organize lots of information? Think especially what you do for a math class.
Tables?
Tables. Expect lots of tables. And I'm going to show you what these tables look like. Conveniently, they're going to look like the same thing every time. But just expect that we are going to have to utilize tables, because if we don't, our information ends up all over the place, and it's going to be difficult to take our information from the equation and make it into a graph like we see on the screen. All right. When you finish copying things down, have a staring contest with somebody on the screen. And don't be embarrassed, because they don't know who you're staring at. It's one thing unlike being in person. They know who you're staring at if you're staring in person. All right. Only missing one person now. Cormac, I don't know where your family works, but I'm impressed with all the books behind you.
Yeah, I'm at my dad's firm.
Yeah. And I was checking out Sathia's background too and thinking, that's where I want to be. I'm not sure where it is, but it just looks like you'd have food behind you.
I'm at my mom's nutrition club.
Nice. Yeah, I've only had a couple bites of breakfast this morning, so that one sounds even more tantalizing. All right, can I scroll? For those of you that just joined us, I did forget to start the video on time, but it started now. You can catch up in the last minute at least. I didn't see any objections, by the way. Okay, so we are going to have our first challenge right here. We're going to graph the equation, and each equation I give you will get a little harder, but not a whole lot. We're going to graph this equation without a graphing calculator. So if you have anything that will graph a function, put it away. We'll check our work at the end, but I don't want you to pay any attention to it right now, because I just want to show you. Check out these methods while they work. So we've got a couple things we need to look at. First, we need to think about yesterday's lesson, or Tuesday's. We know that last time we talked not just about the first derivative, but we talked about sharp points and endpoints. So, first, as we analyze our function, this function is a polynomial. Polynomial because it's got multiple terms, and those terms, the x's, have whole numbers as exponents. And polynomials, by definition, there are no endpoints, and there are no sharp points on a polynomial. So those are two things that we did cover last time that we don't have to worry about on this problem, but we will have to on future problems. So I'm going to make a note of that before I even get started with this first derivative test. All polynomials follow this. There are no endpoints, no sharp points ever on a polynomial. Second, I'm going to apply what we call the first derivative test. And to do that, we're going to take the first derivative. And because we're no longer on the basic skills test, we do have to simplify everything. And with the first derivative test, what we're going to do is we're going to set our equation equal to 0, and we're going to start by finding our extrema.
Why didn't we take the derivative of 3x squared?
I did take, because this was the original function.
My bad, sorry, I forgot.
Yeah, so 3x squared is the derivative. No, still a good question. If you missed something, because I had scrolled at that point, so we couldn't see the original one anymore. And, by the way, next class we're going to teach you the second derivative test, and how to apply that to the graph. Which means we will be taking the derivative of this derivative next class. Alright, so I'm going to take my equation that is the first derivative. I'm going to set it equal to 0, and I want to solve. Now, there are two ways you can solve this equation, and one is definitely superior to the other. You could solve it like an ogre, which means you start moving stuff around, multiplying and dividing until you get x by itself. But that actually is the inferior way, because if you do that, you're going to lose one of your answers. So when I say solve it like an ogre, I mean you could move this over here. Let's see, I could divide both sides by 3. I could divide both sides by x. And so that would go away, that goes away, that goes away. And I would be left with x equals 1, because I get 1 left on this side. But you actually lost one of the answers. It's a quadratic, so I should have 2 answers. So what is a superior way to solving it like an ogre, where I won't lose an answer? Cormac, I don't know if your hand was up or not, but... Okay. It starts with an F. Factor. So, my other option would be to factor, in which case I look to see what I have in common between the two. I guess now that I'm thinking about it, there's a couple other ways I could solve it, but let's focus on this. And I remember there's that rule that says if a times b equals 0, a equals 0, or b equals 0, and we have two things that are multiplied together to make 0, so we set each of them equal to 0 to see what they yield. And of course, since it's a quadratic, you also could use the quadratic formula. You could complete the square. That'd be fine. So, anytime you have more than one terms, yeah, Nolene, I will in a second. Anytime you have more than one terms, that's when you want to avoid solving it like an ogre. If you have more than one term with an x in the problem, rely on other methods you've learned. And Elena, as soon as if I were to scroll up right now, somebody else would say, "Can you scroll back down?" So, I will again just in a moment. And this is where the cameras on the faces really help me, because then I can see if you're copying stuff down. When they're aimed at the wall or the ceiling, I don't get that feedback. Or at the desk behind you. Alright, does anybody still need this? It looks like you're done copying down, but it's hard to tell. Gabe, did you finish copying it down? Okay. Alright, so what did I get? I got 0 and 1. So I find my extrema are at x equals 0 and x equals positive 1. But are they minimums or maximums? That is the question. And this is where now the table's going to come in handy for us to be able to analyze what is what. So I'm going to scroll down a little bit. Melina, did you get the stuff up top you were looking for? Okay. I think I've got room for this. All right, so third, and this is the second part of the first derivative test. I'm going to make a table, and I'm going to put the exact same stuff in the table every time. I want to analyze the intervals before, between, and after each of my extrema. I want to pick a test value in that interval to see how the derivative behaves. And when I put it in, I want to know what is the sign of that first derivative in that location. And I want to have a conclusion that I can use on my graph. Every textbook you look at for calculus will have these 4 things, and they'll organize it as a table. And my intervals, like I said, I'm going to be using these extrema. I'm going to say I want to go from negative infinity to the first extrema. Then I want to go from the first extrema to the second extrema. And then I want to go from the second extrema all the way back up to infinity again. And this is the table that I'm going to use to do my analyzing. And I'll scroll in a second. I just wanted to remind myself, 3x squared minus 3x. So, just since it's not going to be on the screen, so just shout it out. I need a number between negative infinity and 0. Give me a number that works. I'll take the first number given to me. -4. All right, I need a number between 0 and 1. 1 is
0.3.
on the or like it's on the end point of the interval, so I want it to be between 0 and 1. I don't want it to be right at 1. All right, and somebody else I think said 0.8, but it was while I was talking and 0.5 came in, and I don't know if you really said 0.8, and any number will work though. All right, give me a number between 1 and infinity. 500. Okay. All right, so what we're going to do is we're going to plug these numbers into our function. You don't even need to know what the answer is. If you find the answer, that's not a bad thing. But I'm going to find the derivative at -4 the derivative at 0.5, and the derivative at 500, and all I care about is do I get a positive number out or a negative number out. What the number is, I don't even care. So, here, negative 4 squared minus 3 times negative 4, that number becomes a positive number, so I get 3 times 16, very positive. Here, negative times a negative gives me a positive 12. Don't even have to take it any further. I know that's a positive number. Do you agree with me? Keaton says yes. Don't even have to take it any further. That's good enough. Put a positive there for the sign of my derivative. Take the mathy part as far as you have to go. And if you feel more comfortable grabbing a basic calculator to find these answers, that's okay too. Just no graphing calculators yet, like I said. Don't graph the function yet. Let's see. 0.5 times 0.5 should be 0.25. Minus 3 times 5 would be 15, so this looks like probably a negative 1.5. And it looks to me like if I distribute that, that'd be 0.75. Looks like this one's bigger, so I'm getting a negative out of that. And by the way, I'm just demonstrating for you what it would look like without a calculator because, again, you can't use a calculator on the entire AP test. Some of these things it would be reasonable to ask you to reason through without a calculator. So I'm just trying to show you how to do that. But if you need a calculator, no problems. No problems whatsoever. Now 500 is so big, I bet I can figure out pretty quickly which one's going to win. Because let's see, 500 squared, that'd be a 25 and then 2 zeros, so 4 zeros. That's huge. This one definitely beats out the thing that we're subtracting from it. Sounds to me like we get a positive out of that. And again, feel free to check me on a calculator. Now my conclusion is, am I going up or down? Am I increasing or decreasing? I'm going to use the words increasing and decreasing instead of up or down. So when my sign of my derivative was positive, was I increasing or decreasing? Keaton's telling me. Remember up here. When my sign of my derivative was positive, was I increasing or decreasing? Show me with your fingers, like Keaton is. All right, I've got 3 people. 4 people, 5 people. And Trisha maybe is showing me, or maybe she's holding her head. All right, I got it from enough people. When it is positive, you are increasing, you're going up. And when it's negative, what are you doing? All right, got it from Francisco, Keaton, Mia, Annie, Melina. You are decreasing. All right. So, last, I am going to say, let's go ahead and find the f of the extrema. Or even better yet, let's not call it extrema. Let's, because of what's coming up next class, let's find the x of the critical points. And put the graph together. So, just as a reminder, the original function, which you actually should have in front of you, was x to the third minus 3/2 x squared. I'm going to have to do some scrolling back and forth. It actually should be easier for you if you're all on the same page. So in other words, what I'm saying is, let's find these values. And so we can have some actual points that are anchored to the graph. And once you have that, we're going to go reference our table. And our table told us when we were going from negative infinity to 0, we must be increasing. Going from 0 to 1, we were decreasing. And then after 1, we start increasing again. So that sounds to me like I was increasing, decreasing. Oh, let's maybe not go quite that far. And then I started increasing again. And now is the point where I'm going to check myself. I'm going to change my window to match what I graphed. So I went from like -2 to 4. And I went from about -2 to +2. How'd we do? Can you see where this method, well, yes, it does take some work, definitely more work than just grabbing your calculator. Can you see where this method would be more helpful than making endless tables? It will go faster than that, than trying to be like, okay, -2, -1, 0, 1, 2, 3, and then making sure you don't miss anything that happens between those numbers. Keep in mind, calculators are actually relatively new. I know you've had them your whole life. I've had them my whole life. My parents have had them pretty much their entire lives. But in the history of the world, that's not that long. I remember talking to my grandpa once. He was an engineer. Worked on a lot of big projects up at the lab in Idaho. And he was probably in his 30s or 40s, I think. He didn't tell me how old he was. But I'm going to guesstimate, he was probably about that age. The first time one of his coworkers bought a calculator. And this calculator, he said it cost him $500. The calculator he had was at most as powerful as the one you have on your phone. But he spent about $500 for just a basic scientific calculator. And my grandpa said that he became the most popular guy in the lab. That there was like a 2 to 3 week waiting list to be able to use his calculator for calculations, because it actually was still faster to wait for the calculator for your turn than to do some of these calculations by hand and with a slide ruler. So, all of these methods up here, for hundreds and hundreds of years, this was the faster way to do things. Now for you, of course, it's not the faster way because we have the technology, but for you, the purpose of this curve sketching is just so you can become more familiar with how the derivatives will apply so that we can use them in other ways. So, all I have today is I've got 1 or 2 more examples like this, and then we're going to be done. Yeah, I've got 2 more, it looks like. And each one will go faster and faster. So, how are we doing? Am I hurting your brain too much today? Because I know I have in the past. I think today's lesson is a nice little respite. Is that the word I'm looking for? From some of that. All right. Let's try another one. And like I said, let's make it a little more complicated. Not much, but a little. So my first question for you is, you understand what the equation of x looks like. You understand what the equation sine of x looks like. We usually don't put them together, but I think you can still reason your way through this since we're not multiplying or dividing or anything like that. We're just adding and subtracting. Do you expect any sharp points on this graph? Keaton is telling me very emphatically, that or else he's having fun with his hair. Cormac's given me a slightly smaller, me is a little smaller. There's nothing about this that indicates we should have sharp points. When you're adding and subtracting the terms of things that are already smooth curves, you're going to get another smooth curve out of it. Really, it's only when you start, especially multiplying, or not multiplying, but dividing, that you're going to have to worry about potential sharp points. So we can expect no sharp points. But because it is on an interval, there are endpoints. So let's find the y values of those endpoints. We don't need them yet, but we'll need them at the end. And if you remember your unit circle, that will be helpful on problems like this, especially if you're trying not to rely on a calculator. If you're using a calculator, make sure you're in radians. But the unit circle is something I know everybody's gone over, but I know that doesn't mean everybody's super proficient at it yet. Let me pull up a unit circle so I don't have to rely on my drawing skills to show them to you. All right, now on the unit circle, do you remember, does sine go with the x coordinate or the y coordinate? Annie's telling me. Helena told me. Some of you visually on the screen and some of you verbally in the chat. One of you go ahead and shout it out for the rest of the class. Either Nelina or Annie. Your answer was correct. Go ahead and tell everybody. Say it again. Sorry.
It's y.
It's the y coordinate. And so
0.
You're giving me the answer, Cormac. So on the unit circle, your cosines go with the x coordinate, and your sines go with the y coordinate. If you don't remember why, please send me a message and I'll make a video all on that to teach you the unit circle. Because it definitely is going to be expected that you understand the unit circle and can make your own for the AP test. Okay? So we are going to use the y coordinate at 0 radians. And so that is going to give us a value of 0. And then we're going to also take the sine of 2 pi, which conveniently 2 pi is at the same place as 0. So we're going to use the same y coordinate. So this happens to go away in both cases. And again, if you don't remember the unit circle, if you don't think you can produce one from memory or process, really. All right, and I've got one request to make one. Absolutely. Because that, once again, it's worth it. And I have an activity that if you had me for math last year, then I don't expect you to remember how to do it. But it was after we went into quarantine, and I had you do a paper folding lesson, where then you had to take the paper and like scoot it around. It was a circle, you had to scoot it around the other circle and mark spots. For those of you that had me for math last year, you might remember that. That was what this is all about. All right. And what I'll actually do is I'll just take the video I did for my lesson last year and I'll upload that. It has some materials so you can make your own at home. Because I think the hands-on helps me understand. My teacher, when I took this class in high school, showed me a unit circle and said, here it is, memorize it, it'll help you. And that was it. Like, he never told me how to use it. He didn't tell me how to make one. He just made it sound like I had to memorize it and it was going to be helpful. And I don't memorize well. This is actually a funny thing about me. I can do crazy math. People are like, you must be so smart. No, I've got the memory of a goldfish, okay? So I cannot retain information. Those of you that are in the play and can do that, like, I admire you so much. I can't even, that would be my worst nightmare, to try to memorize lines and hold it in my head. I can't do that. And so the idea of memorizing the unit circle just was awful. Trying to remember where all the angles went. Until I found a process to help me replicate it. And I can do processes. I can problem solve. I can work my way through steps. That's where my strength is. And so I'm showing you how to do that so you can avoid the whole just memorize it. And I'll show you that video that I made for the Math 3 kids last year. That's why I didn't scroll. That's right. We'll get back to that. All right, so conveniently this also goes to 0. So I get 0 here. Here the 2's cancel out and I get just pi. Now I'll scroll and get rid of all that stuff that I wrote on with the zoom annotate, since it does not go away. All right. So let's see, we've got 0 to 1, 0, 2 pi. Let's go ahead and call that 2 pi, which means this would be pi. We have so far these endpoints at 0, 0, and at 2 pi, pi. Not enough to know what's going on between them. That's all we've got for the graph so far. And even then, I actually already labeled this inappropriately. Let me scroll up because we didn't use this sort of bracket last time. But when I have the rounded parentheses, do you remember what that means? Some of you said that you did learn interval notation. All right, Annie told me in the chat. When you see this, it does not mean equal to. It means just the less than symbol. So if I'm using just the less than symbol, did that a lot like meaning forgot to put the open dot or use the interval notation? To Cormac. Used interval notation? Perfect. That's good, because honestly in college they use mostly interval notation. Alright, so I've got this much down, but I don't know what's happening in the middle. It's time to apply the first derivative test. And the derivative of 1/2 x gives me 1/2. The derivative of a sine gives me a cosine. So here is my derivative. I want to then set my derivative equal to 0. So I'm going to take that derivative, set it equal to 0. In this case, because there's only one x term, it is most appropriate to solve like an ogre. So I'm going to move my terms so that on one side I have all the terms that have x, on the other side I have all the terms that do not. And at this point, because I'm going to try to do this without a graphing calculator, it's going to be most appropriate to pull up the unit circle again. Did I close it? I must have closed it. So we're trying to find the places where your x value, because we said the x coordinate, it goes with the cosines. We want to find the places where your x coordinate is 1/2. Where do you see that happening? At what angles? And there should be 2. And tell me in terms of radians, not degrees. Okay, Annie gave me one of them. Francisco gave me both of them. Annie gave me the other one. Nalina gave me 1.5 of them. All right, so our x coordinate equals 1/2 right here and right here. And that is a lot to look through. So the angle in radians is what I'm looking for out of that. So pi over 3 and 5 pi over 3. If you don't remember the unit circle, but you remember your special triangles, you also can make a right triangle where you do want to make sure your theta is in the bottom left side. And you can say, okay, cosine is also equal to the adjacent over the hypotenuse. So adjacent over hypotenuse. You can use Pythagorean theorem to finish this off. And it is a special triangle, which I really, really do hope your teachers at least spent some time with you on. And then you may or may not, again, I hate memorizing, but you may or may not have memorized that this triangle is a theta equals 60 degrees triangle. And if you convert that, you end up getting pi over 3. And then you think about, you still end up thinking about the unit circle, because we're looking for the cosines equals the positive 1/2. So in other words, x coordinate has to equal positive 1/2, so you're going to have 1 up in this quadrant, 1 up in this quadrant. Anyway, it's a process. Ultimately, what it comes down to is, it's hard to see. Yeah, what I wrote was just small and sloppy. That's okay. What I'm trying to get at is there's more than one way to do this, but it is going to rely still on a knowledge of the unit circle. So if you have trouble with that, I'll look for the video right after the class and I'll upload that to today's lesson video along with what I'm recording now. Anyway, alright, so these are the values. These are my extrema. My minimums and maximums. I'm going to use them for my table. And you will need to make this exact table, but of course with the new values in it, every time you do one of these curve sketching problems. And when you do your homework, please do take note. You'll see in the homework, I have changed the instructions from the book so that you are doing exactly what we're doing in class and practicing this on your own. Alright, so let's see, we were going from, our interval was from 0 to 2 pi. So I'm going to go from that 0 to the first extrema. From the first extrema to the second extrema. And from the second extrema to the end of the interval that I care about. I'm going to write the derivative down here again so I can still see it. Still a fair amount to put together, but if you get used to the process, we as human beings, we like schedules, we like process, we do this, then this, then this, then this. Do this, then this, then this, then this. And follow the routine. And in your homework, you'll get some extra time. This is only the second problem we've done. But as you follow that routine, it's going to become pretty second nature to you. Alright, just shout it out. And let's maybe pull up the unit circle again, just so you can be more confident about the numbers you're picking. Give me any angle between pi over 3, or between 0 and pi over 3.
Pi over 4?
Pi over 4, okay. Give me anything between pi over 3 and 5 pi over 3. So in other words, I'm looking for anything from here to here. Keaton tells me pi. I like pi. It's nice and easy. And then give me anything that goes from 5 pi over 3 to 2 pi. In other words, right here. Which I just totally covered it up. Sorry.
7 pi over 4.
7 pi over 4. Alright, so when we find our sine, we're going to plug these values in to our derivative and look and see, do we get a positive or negative out? So So 1/2 minus the cosine of pi over 4. That is scary. Cormac, what's giving you the countdown? Is it Zoom? Nope, he's gone. Okay. He wrote me in the chat. It's giving me a scary countdown. I have 10 seconds. I don't know what that means. But let's set all these up. And from the unit circle, we're going to pay attention to the x values on each of these. So at pi over 4, at pi, and at 7 pi over 4. So we get 1/2 minus square root of 2 over 2. 1/2 minus a negative 1. And 1/2 minus another square root of 2 over 2. You see where I'm getting those? Welcome back, Cormac. And I'm going to go back over these now with the non-zoom paint, because as soon as I scroll, because I'm using the zoom for what I just did, I'm going to end up losing all that. So while you copy, I'm going to copy. So I will say too, when it comes to things like the unit circle, when I learned it, didn't make any sense to me. Why would the teacher put me through that? And then when I took calculus, I got to know it better. I got to know algebra better in calculus too. We're doing so much of the using of these subjects and not just regurgitating, that you really are going to learn all the math you've ever learned in your life, a little deeper than you've ever learned it. And then the trade-off to that too is the calculus then will be the newest stuff. And you're going to have these moments of, oh my goodness, that was so hard. Thank goodness I'm never going to do that again. And then the next class you take is going to use the calculus. And you're going to go, oh, the calculus was the easy part. But this new subject, thank goodness I never have to do that again. And you're going to repeat that with every math class you take. My brother and I were actually just talking about that 2 weeks ago about, because he's working on his master's degree in statistics right now at the U. And he was like, you know, when I was taking some of these calculus classes, I was like, this is so hard. And then I went on to the next class, and I'm like, oh my goodness, I wish I was back in calculus. That was so easy. So, but always just push yourself. Again, push yourself. He's going to make much more money than I do, because he's pursuing a career path nobody wants to do because they don't want to do the math. If you do math or are willing to put up with stuff nobody else wants to do, you'll make the money. Which is why the best job security that you can find is either in math or plumbing. Because nobody wants to deal with what goes down the pipes, and nobody wants to do math. So if you go down in either of those paths, you're going to be set. Alright, now here, this one's going to be the easiest one to solve. 1/2 minus a negative gives me a plus. That obviously gives me a positive. I've used the square root of 2 enough to know that it's approximately 1.4. So if I have 1/2 minus the square root of 2 over 2, they have the same denominator. I can think of it like this. That's like saying 1 minus, roughly like saying 1 minus 1.4. And we can see that the second half of that number is the bigger half. That's going to give me a negative number. And then this last problem tells me the exact same thing. So I end up with a negative, a positive, and a negative. Anytime it's a negative, I'm going to decrease. Anytime it's a positive, I'm going to increase. So I'm going to scroll back up to here. By extrema, we're at pi over 3 and 5 pi over 3. You can, of course, write this back down, but I had already started the graph here. So I found my extrema at x equals pi over 3 and x equals 5 pi over 3. Very conveniently, all I need to do is split my pi sections into thirds to find where those are located. And I can go 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3. And I don't know what those y values are yet. Personally, I think it is a good idea to go ahead and find them, which means we need to come back to that original equation to find exactly where they are and find the f of pi over 3 and the f of 5 pi over 3. So 1/2 times pi over 3 minus the sign. Give myself a little more room. Of pi over 3. Don't worry about getting this exact. Although I could see us probably wanting a calculator for this, because we're going to be adding things with pi's to things without pi's. We're dealing with sines here, so it's the y value I want at those angles. Oops. Forget that that goes away. Alright. Square root of 3 over 2 and negative square root of 3 over 2. Go ahead and get those values in. And let's see here. Pi over 6 minus that. 5 pi over 6 minus that. Yeah, that one I don't know off the top of my head, certainly. That is one I am going to rely on a calculator for. Let's finish the problem though. Minus the square root of 3 divided by 2 and plus, because minus a negative is a plus, the square root of 3 over 2. Alright, and I'm going to take this off the screen, my calculations, so that I can still see them when they disappear. But this one was about negative 0.34. This one was about 3.48. Which, no reason I'm going to try to be exact on that, on this graph, especially since I'm dealing with pi's. But this is a little bit bigger than 3.14, so it is going to be a little bit bigger than our pi value that I've got on my graph, whereas this one is going to be slightly negative. So I think it's reasonable to put it maybe right about here. And of course, to compare it to what I have with my derivative test, I know I'm going to decrease, then increase, then decrease, which I can already see coming out in the graph here. I'm going to decrease, then increase, then decrease. And we can check ourselves. Right there. Do you have one more in you? Me is being honest. It has sharp points in it. Still no? Says Keaton at least. Alright, I'll do a video on this one. I'll let you go and I'll do a video quickly. But, before you go, I'm going to give you a heads up. By the way, actually, no, I'm going to do it. You want to know why? Because when I make these videos, I can see how many views these videos get. You know the last time how many views my video got when I did a special video for you? Andrew's got it. Cormac, there were 2. 2 of you watched the video after I said, okay, I have another example. I'll do this for you just as a video, just for you. Make sure you watch it. No, nobody watched it. I'm not giving you an option. Are you crazy? All right. It'll go fast, though. All right. So, on this one, when I look at the question first, I can say I'm not super associated with 2/3 power. I can say I'm not sure from the get-go if it has endpoints or sharp points. Told you it does because I finished the problem already, but at the get-go, I'm not sure which one it has, or if it has either. So I need to just be aware of that. It's a possibility it could come up. Second, I'm going to take the derivative. Now, in this case, when I set it equal to 0, very conveniently, the bottom of your fraction can never make your function 0. So when I set it equal to 0, all I have to actually care about is the top. And that one gives me a pretty easy answer. There's going to be a critical number here. Probably an extrema. But check to see where the denominator equals 0 because that could give me a sharp point. So I analyze these two separately. And very conveniently, the only part here that matters that could set me equal to 0 is if I get the inside of the parentheses equal to 0. And again, it's always a better idea to factor than to solve this like an ogre when you have a squared, so you don't miss one of your answers. These are still going to be critical numbers. Up here I'll put probably extrema. So, when the denominator does not exist, or where it equals 0, I should say the first derivative does not exist at these points. If the function itself does exist, we have sharp points. If the real function doesn't exist, then your derivative wouldn't exist there either. So we'll need to double check to see if those points work in the original function. But if they work in the real one, but or if they work in the original function but not in the derivative, is that good, Nalina? Then they are sharp points. If they exist on the function but the derivative does not exist, it has to be a sharp point. So I do need to take into account all of my critical numbers, whether I think they're extrema or sharp points, in the table that I'm going to have. And Alina, tell me when I can scroll, because I'm going to need room for that table. Okay. Oh, wait. Yeah, give me a thumbs up when you're ready for me to scroll. Okay. Alright, so 0, -2, and 2. Those are my numbers, which of course on a number line go in that order. So, and again, the more you do the table, the more second nature the order of those come. I want to start from -infinity, because unless they tell me I have an interval, I'm going to assume that I can. And go to the first critical number. Then from the first to the second. From the second to the third. And from the third on to infinity. I'm going to write this down here again so that I can remind myself, because again I can't see the whole thing. Okay, and I'm going to pick the test values this time. No, I went super fast through that. Didn't even care about what the actual numbers were. I just looked at the parts that could make me positive or negative. And so there in the red below each function, I was just checking negative 3 squared gives me 9. 9 minus 4 gives me a positive number. Don't even care what that positive number is. I know I'm going fast, but it's because I'm watching the clock.
Wait, f of 2 isn't 4 supposed to be squared?
So I'm going back to the original problem, which was x squared minus 4 all to the 2/3 power. And I did kind of skip a step here, but I plugged in 2 and squared it and got 4. And 4 minus 4 was 0, so any 0 to any power will give me 0, including a 2/3 power. And then here, again, I get 4 minus 4. And so those two do exist. Was what I was going for there. Alright, and I'm not going to find all of the y values, although I did just find those two. So at negative 2 and at 2, we did get 0 for both of those. And so I know that it's got to be a sharp point. I know at 0, I'm going to have an extrema. And I know that I'm going to decrease first to get to this point. And then I'm going to increase. But it's not going to be sharp up here. Let's maybe not make that look like it's going to curve back down. And then I'm going to decrease. And then I'm going to increase. And let's see, my original function was... And so this function of the ones that we graphed today definitely is the one I'm least familiar with. Like, it's just about one I use on a regular basis. But, check how well we did. Now, if you start watching the videos I make, I won't hold you after when we have these moments. Okay? Which you're going to have no choice soon, because I'm only 2 weeks away from my delivery date. So, and they could come anytime. So... for your homework, follow the instructions that I put on Canvas and not the ones in the book. You'll see that before you even see what problems you're assigned. And then also, I do have 3 or 4 word problems I gave you. I did give you some hints on Canvas about just reminders, things like when it gives you a position equation but asks you about velocity. the derivative of position is velocity. And if it's asking for a minimum or maximum value, that's finding the extrema. You take the derivative, set it equal to 0, find it that way. If you get stuck, remember I've got office hours tomorrow from 9 to 11. Just let me know. And not only is synchronous part of class done, but class part is done. So let's take roll.